Alright, good morning everyone. We'll start class in 1 to 2 minutes time. Good morning everyone, and today's lecture, which is our final lecture for this course, is going to be on audio fingerprinting, and in particular the contents of this lecture are going to be focused on the last question in your final exam, being with 20 marks out of the 100 marks. So it's quite important that you pay attention to what we're delivering in this lecture in particular, and ask any relevant questions that if you have anything that you don't understand or require some clarification, it's quite important to ask it at this point in time during the lecture. So feel free to interrupt at any point and ask those questions, so that way you can get all the clarification that you require and so forth. So what we're going to be focusing on today is seeing how an example audio fingerprinting system works, as to what is an audio fingerprinting system, what is its application in the real world, and how can we use all the previous techniques that we learned so far in DSP into creating this system and actually using modifications or actually applying it to other forms of DSP itself. Alright, so let's get started. So the typical situation for any audio fingerprinting system is that it's used basically to find song matches in particular. So your general situation is like you might be hearing a song on the radio if you go out somewhere and it's playing, and you may want to figure out, okay, well, who's the artist who sang the song and what's the name of the song and so forth. And it's too cumbersome to try and call the radio station, because first of all, trying to find the radio station number is a problem, and it isn't fast enough, because by the time the song is finished playing, and you probably finally get through the radio station after calling them, they'll be like, well, which song are you talking about? And then you might have to hum something and whatnot, so it's a little bit somewhat embarrassing as well, and so forth. So it's possible for us to actually use a DSP system or create a DSP system to actually find these matches, and it's been done like in a matter of seconds. So the presented system that we're going to be focused on here is showing how we do the fingerprint extraction method, being that whatever song is playing, we actually extract out a fingerprint from that song in a matter of seconds using that as our sample. And then how do we use the sample here to search through a database of fingerprints or a database of songs themselves to find a required match. So fingerprinting systems aren't something relatively new, because they have existed for hundreds of years. And quite back in 1893, Sir Francis Galton was able to prove that fingerprints on the human beings, they aren't alike. And Scotland Yard basically implemented the system afterwards, 10 years later, to identify people. And even so, years before that, all the way in the BC era, sorry about that. Yeah, years before in the BC area, The Chinese emperors used to be using thumbprints to sign important documents because they realized that thumbprints themselves were a unique form of identification. Now, a human fingerprint, whereas it's somewhat visual in nature, this actually differs from a textual summary, and you really can't do any sort of reconstruction onto the original from like a textual summary versus a human fingerprint. And basically, we use the idea of how the human fingerprint is unique, and how we can somewhat make a textual summary unique in some form or fashion to actually compute a fingerprint of a multimedia object. And these unique identifiers, also referred to as UIDs, which basically says, okay, for our particular application, the unique identifier for this particular song will not be the same as any other song throughout the entire database. So that gives us the possibility that we can find a direct match, meaning a one-to-one match, for only that unique identifier. So the objective of multimedia fingerprinting is that we need to establish what we refer to as the perceptual equality of two multimedia objects. And our fingerprints here will be serving as an index to our metadata, where the metadata would be like the artist who sung the song, the name of the song, the genre of the song, the beats per minute, and so forth and whatnot. So the advantages of using the fingerprints over direct multimedia content itself is that we have reduced memory and storage requirements, so it becomes possible for us to store a huge database of fingerprints representing like millions of songs. It's very efficient to compare these because anything like irrelevancies and perceptual quality are removed. So like if one person hears something different from the other. And effectively, because now it's a digital system, depending on how fast the hardware is, and if the hardware can operate in parallel, that means we have very efficient searching because the size of the data set in comparison to the hardware requirements is smaller in nature due to the reduced memory and storage requirements. So it becomes very fast to search this entire database depending on the hardware and stuff that's used to actually do this searching. So a general audio fingerprint is basically, it's in layman's terms, a short summary of any audio object. So it could be like 3 seconds of entire song, 3.5 seconds, something like that. Basically a really small sample of an actual long audio file. And we also refer to these as cryptographic hash functions, and mathematically we refer to these as H. So H here basically maps to some unusually large object X, where the large object here will be like the entire song, H will just be the sample of the song. Now, any cryptographic hash function will allow some comparison of two large objects X and Y, such that you can have H of X and H of Y being compared to each other. And because it's a cryptographic hash function, the nature of those functions basically means that when you do the comparison, there's a very low probability of error. Now, when I say low probability of error here, there is an error, yes. But this comes like the same approximation error that we saw when we were doing the DFT, going towards the FFT and so forth. The error is so small that it's basically a very small approximation error that can be neglected. So we can set our tolerances such that we accommodate for this really small approximation or probability error in this particular case. Now, cryptographic hash functions are not really a good candidate for fingerprint functions, mainly because cryptographic hash functions is basically trying to match the textual similarities one-to-one. And fingerprint functions basically can have perceptual irrelevancies and perceptual differences, which basically means like, okay, perhaps the song that is being sampled is played 1.25 times the original speed, or maybe it's being mixed with a different beat or something like that. So because it's trying to do a direct match for cryptographic hash functions, this isn't already a good candidate for fingerprint functions itself. And this is quite true when you have different audio qualities in particular. Because the waveforms themselves, when you compare it in time and frequency, they're going to be quite different to each other. So doing this kind of waveform match isn't going to work for this particular application. So we're going to have to use another model of perceptual similarity in order to get this sort of matching to actually occur. So it's possible to model perceptual similarity by some sort of mathematical equality of fingerprints, and this was what we're going to refer to as the construction of our fingerprint function. Now, some applications of the fingerprint functions that you can actually see is like when you're doing broadcast monitoring, connected audio is what we're going to be focusing on today, and filtering technology for file sharing. And this is basically like when file sharing of songs were rampant, so there was a huge illicit trade. And then eventually the copyright holders and the copyright companies eventually figured out a DSP technique to actually start filtering out the copyright material using these fingerprinting functions. Now the parameters that will be used for creating this audio fingerprint system are going to be these 5 parameters here. And we're going to see how do we trade off each one of these 5 parameters in particular. So the first thing is that the robustness, being that can we still identify that audio clip after severe signal degradation? So if noise is introduced into the signal, if the signal quality itself is very low. The reliability of the system is how often is the song going to be correctly or incorrectly identified. Meaning that, okay, let's say 9 out of 10 times the system will identify the song correctly. I mean, that's at a 90% chance that you will get the correct song and so forth. That's what you refer to as the reliability factor. The fingerprint size is going to be, okay, we have fingerprints, yes, that's what we're going to be creating for our system. How much storage is going to be required per fingerprint? And then, in general, how much storage is going to be required for the overall system, leading to how many songs can we identify. In creating this fingerprint size here and observing it, we also need to refer to something that we refer to as the granularity of the audio itself. Meaning how long is going to be one of these fingerprints in terms of time. How many seconds of audio is going to be needed to identify some sort of audio clip to actually do a fingerprint match. And then finally, for our system, we need to figure out, okay, what's going to be the search speed and the scalability. And that basically means how fast can we find a fingerprint in our fingerprint database itself. So, for instance, let's say our system scales well, meaning that such that as our database grows, the time taken to actually find a fingerprint is going to be very small. That means it's going to be something similar to like a log function, where basically the search time is just going to plateau even after we reach a maximum size, and the size keeps on growing. So that's actually something that will be ideal for an actual fingerprinting system. So the features that we need to focus on, being these perceptual features for creating our audio fingerprinting system, we're going to have to focus on what's going to be the genre of our music, the beats per minute, also referred to as BPM, and something also referred to as mood, which is very subjective in nature, meaning that doesn't make you feel happy, doesn't make you feel sad, and so forth. But these 3 things are going to be what we refer to as semantic features. And then the non-semantic features, which is going to form the core of our system, is what we refer to as the mathematical nature of our signals. And in this case, it's going to be what we refer to as audio descriptors themselves. So semantic features, because they're so subjective in nature, they're more difficult to compute than non-semantic features, because that comes like if we're trying to create a mathematical match to something that isn't numerical in nature to begin with. And semantic features in some cases are not universally applicable, because BPM itself doesn't apply to classical music, because classical music refers to something like 3 out of 4 beats, or 4 out of 4 beats, or 6 out of 8 beats. And BPM in modern days is like 90 beats per minute, 120 beats per minute, and so forth. So BPM actually does not apply to classical music itself. Now, because we're using the non-semantic features here to form the core of our system, that means any of these digital fingerprints can actually be represented what we refer to as bit strings. And because they're not bit strings, and that means that they're digital in nature, we can actually do similarity measures using addition, subtractions, and multiplications. And we can break up these fingerprint streams, being our bit strings here, into small atomic intervals, which we're going to refer to as sub-fingerprints or frames of the signal. So any audio signal for our system here that we're going to capture, being that it's going to be 3 or 3.5 seconds to form our fingerprint, is that it's going to be segmented into frames that allow for faster processing. And for each frame of this audio signal that comes in, we're going to be computing a set of features. And these features here that are listed, they're going to be invariant, meaning that they're not going to be so susceptible to corruption in signal degradation. So these features here are going to be what we refer to as the Fourier coefficients, which we have absolutely seen in our lectures. Something that we refer to as mel frequency cepstral coefficients, or MFCC, spectral flatness, sharpness, and linear predictive coding. There are also a few derived quantities, being derivatives of combinations of these 5 here, which is going to be like derivatives, means, and variances of the audio features. They can also be used, but we're going to be focusing on these 5 particular features here. And in our example here, we're going to be focusing on the Fourier coefficients in particular. So the framing system that actually happens when we actually sample our audio signal, and then the signal here is broken into frames. Remember, this is still with respect to time. So we're going to have to get this with respect to frequency now by doing the Fourier transform of each one of these frames that come in. After we finish the Fourier transform, we take the absolute value of those frequency components, and then for each frame here, we're going to do the same band division, energy computation, and bit derivation in order to segment out this entire audio signal here into its frequency representation frames using their absolute values. So I'm going to just repeat this again for anyone who probably missed the explanation. The audio signal that's coming in on the input here that we're sampling is going to be segmented into frames. Each frame is going to undergo the Fourier transform to change it from the time domain representation to the frequency domain representation. Sorry about that again. Right. Once we have the frequency domain representation of each frame, we perform the absolute value of each one of these frames, because remember, this is going to be a real and imaginary value, so we want to be focusing on the absolute value in frequency. And then for each frame here, I mean, like, this is the first frame, second frame, all the way down to like 31st frame and the 32nd frame and so forth. It's going to undergo band division, energy computation, bit derivation, and so forth in parallel to form of frequency domain representations here to create our fingerprints for the audio. Now, it's possible to map these features here into a more compact representation using something referred to as hidden markup models, which is basically a quantization feature, which is where we get our sub-fingerprints or frames that we actually started with. Now, one frame here, remember, this is like a fraction of that audio sample, and that isn't going to contain enough data to identify any sort of audio clip. So the combination of those several frames there is going to make up what we refer to as our fingerprint block, which we will be using to match our audio sample to our stored audio signal in our database. Right, give me 1 second, guys. Allergies are acting up this morning, so I do apologize for that. Alright, so the general streaming approach when we're doing this to explain our diagram is that when that audio signal comes in from our input, we're going to be using something referred to as 32-bit frames that's going to be extracted at 11.6 millisecond intervals. So each frame there being 32 bits, that's going to represent the size of our frame. The fingerprint block itself is going to consist of 256 subsequent frames, which basically, if we do the multiplication and maths here, we're going to get a granularity of approximately 3 seconds to form our fingerprint itself. In segmenting that audio signal that comes in here to create our fingerprint, we need to segment this into overlapping frames. Because as we saw when we were doing the short time Fourier transform for a real-time signal, we need to make sure that we have that signal overlap in order to compute our fast Fourier transform accurately as the signal is coming in real time. So the audio signal here is going to be segmented into overlap frames where we have a length of 0.37 seconds, and we're going to be weighting each of these frames here using a Hannon window, with an overlap factor of 31 divided by 32. And in the worst case scenario where we will encounter some sort of aliasing, the frame boundaries used during identifications are going to be 5.8 milliseconds off. So timing is a little bit of an important issue here in creating our frames itself. Now, the most important perceptual audio features are going to be located in the frequency domain. That's why we transform all those frames from the time domain into the frequency domain. And we're using the Fourier transform on every frame to get its spectral representation. And the reason why we use the absolute value of that spectrum representation of each frame is to actually calculate the power spectral density of each one of those frames. Now, to extract the 32-bit frame itself, we need to make sure that we have non-overlapping frequency bands in order to get a good frequency representation of the signal itself. So the frequency range that is used for our system is going to be from 300 Hz to 2000 Hz. And this is based on logarithmic spacing, where we say like, okay, 300 Hz, 400 Hz, 500 Hz, 600 Hz, and so forth going up. Or we can be like, that way we hit like 1000 Hz, it'll be a 1000 Hz and then 2000 Hz and so forth. But it's basically going to be logarithmically spaced, which is similar to how the spacing is for your board plots and so forth. And the human auditory system, also referred to as HAS, it operates on approximately logarithmic bands. So that's why we do this logarithmic spacing for the frequency range here for our frames. Now, in using the power spectral density to calculate the energy of our signal here, after we do all those bit deviations and so forth, that means basically any energy differences is going to be very robust to any sort of different sorts of processing that we'll be doing on our signal. And the mathematical notation for this is where we denote the energy band of M, of frame N, as ENM, and for any mth bit of the frame N is going to be denoted as FNN. So basically, FNM here, being the mth bit of the frame N, is going to be 1 if we have a good difference between the energy of two frames, and a 0 here if we don't have a good difference of the energy of two frames themselves. So the comparison here is going to be between the M frame and the M+1 frame, as well as the N-1 bit and let me re-explain this. The comparison here is going to be at the nth bits with the M and M+1 frame, and also the N-1 bit with the M and M+1 frame itself. So if we have a match being 1 and 0, we flag this as 1. If the match here is going to be less than or equal to 0, we flag this as 0, indicating that it's not a good match at that point for f of n. So that calculation is what we refer to as our bit error calculation, to indicate, okay, these bits here are good, these bits here are not so good, and so forth, by saying, okay, we're flagging them as 1 being good and 0 being bad. So that's why we do that difference calculation that we saw in the previous slide. And that's going to be used as our similarity measure in order to do the matching for our songs to our fingerprints and so forth. Now, one other thing to note is that for us to get a more efficient search database by reducing our data size, the received audio that we have is going to be downsampled to something referred to as a mono audio stream with a sample rate of 5 kilohertz. And because we're downsampling here, we're not going to get any performance degradation because of that sample rate that we're going to be using. And To make sure that we also don't get any performance degradation, we use 16-tap FIR filters to make sure that our signal itself is still robust. Now, that basically gives us the entire process for how we went about creating our audio fingerprint. And in order to find a match to be such that when we search in our database itself, any 2-3 second audio signals there are going to be declared similar if the Hamming distance is going to be below a certain threshold. So meaning the Hamming distance here is going to be the number of bit errors. So if we have like a lot of matches for that bit errors that we saw, so a lot of ones matching up and also the zeros matching up, that means we have a very high probability match, meaning that this received audio matches to our stored audio in our fingerprint database. Now, we can do a direct match here, yes, but we also can use a probability distribution itself to speed this up. In this particular case, we'll use a binomial distribution, where such that if the probability of the match is more than 0.5, we'll be saying, okay, this is actually a good candidate or a good match for what we have stored in our database. If it's less than 0.5, this isn't a good match. But typically, instead of using 0.5 here, from trial and error, a lot of people tend to use the bit error rate threshold to be set at 0.35 here, or a 35% match in particular. Now, the database search itself, using that binomial distribution, it isn't very efficient to go about doing this for each and every single fingerprint. Where we say, okay, for the first fingerprint that we have stored in our database, we need to find a match for this for our incoming fingerprint, and we want to have to do the binomial distribution for this, and then we have to repeat this for the second fingerprint and the third fingerprint and so forth. But this isn't very efficient, and that's what we refer to as brute force searching here. And that's not good, especially when your database is quite big, because then your search time increases dramatically. So a more efficient search algorithm is going to be required in order to speed this up. And the bit error rate that we just now saw there can only be calculated for a few candidate positions only, meaning that for a very high probability, that's going to be the best matching position in the database. Now, the assumption we make when we try to speed this up is that for at least one frame, we have an exact match at optimal position in the database. And this method will not work if the signal itself is very heavily degraded. So this means that we're going to be relying on the sample signal that is coming in to be of a okay quality or a good or high quality in nature. So the fingerprint database in this particular case will contain a lookup table with all possible 32-bit frames as an entry, and we're going to be trying to match each position of each frame to find a possible 100% match candidate. And once we do find this 100% match candidate, this is going to be a high chance that this is going to be the match that we are looking for to match our sample audio to the audio in our database. Now, in practice, instead of using a lookup table, we use a hash table. But in general, in using the lookup table approach, which basically explains how we went about matching our frames here, it's going to be 800,000 times faster than the brute force approach. So that's a huge speed up in particular. And a hash table even has a greater speed up. In some cases, maybe even twice that of the lookup table, or 3 times, or even greater than that, depending on how well the hash table is coded. Now, there are more efficient ways to prevent or circumvent errors for heavily degraded signals, but that's going to be a little bit out of scope for this lecture. Now, one method to go about it, because we have to talk about it a little bit, but we're not going to go into a lot of heavy details regarding this, is that we saw there that our frames in creating the audio fingerprinting, when they were obtained in order to create our fingerprint itself, we compared and threshold the energy differences using the binomial distribution and energy calculation that we just saw. And we saw that instead of the threshold being 0.35, the energy difference, once it's close to the threshold, it's going to be a heavily likeliness such that the bit received was incorrect. And if the energy difference is larger than the threshold, it's going to be that the bit most likely was correct. And this results in a simple way to generate a list of most probable frames by just toggling only the most unreliable bits. And we get a small speed up in doing this by just using the most reliable frames only to do our searches, but it's still a significant speed up in particular. Alright, so that basically brings us to the end of our audio fingerprinting lecture. Are there any particular questions that need to be addressed at this point in time? And for anyone who wants to read up on the fingerprinting system that we talked about here, this is actually the reference for further information. It looks like we don't really have much questions. There's one other thing I want to discuss here in particular before I close off our lecture for today. And in particular, what I want you guys to note and watch out, remember these frames that we're extracting here from our diagram are going to be 32-bit frames, right? And because they're 32-bit frames, remember, this here is a power of 2. And here? Those are 32 bits, right? So that's going to be a power of 2. And 32 here is going to be 2 to the power, I believe, 3 is 8, 4 is 16, right? So this is 2 to the 5. And because this is 2 to the 5 here, and we're watching this 5 here, when we're doing our FFT for this in particular, that means we have 5 decimation stages. So these particular small things is what you're going to have to pay a little bit of attention to when we're going about actually doing our algorithm itself. So the reason why it's 32 bits is because that gives us a nice even power of 2 to actually perform our FFT on each one of these frames as we're going. And in particular, this here was going to be like, this is this frame. That here is going to be our second frame. And this here is going to be like our 31st, sorry, not 31st. So we started at 0. One here is going to be our 32nd frame. And so forth as we keep on going. So these small little particular things, it's actually what forms the importance of the basis for actually doing our calculations for the techniques that we just now saw. For the techniques that we saw in our previous lectures as well. So these small little parameters actually do play an important part in actually going about constructing our entire system and so forth. Same thing with the fingerprint block itself here, going to be up to 256 sub-equivalent frames. And the reason why we use 256 is because this is also a power of 2 here as well, which makes our calculations for our matching and so forth a lot easier to do when we start doing those decimation stages in particular. Alright, so once there aren't any further questions, if anyone has questions after this live session, feel free to leave them down in the comments below or ask me directly. And like I said, today was basically the last lecture for our entire DSP course. Now, I promise that 4 the solutions were posted up online, as well as some past papers and their relevant solutions and so forth. So those are important for you guys to actually go about and start doing your own practice and whatnot regarding your final exam. And in particular, if there are any questions regarding the final exams, or if you guys do want a live session to go through any particular past papers and so forth, feel free to email me to schedule these, or if you just want one-on-one advice, feel free to email me with your snapshots of your attempts on any of these questions, and I can provide you guys feedback up to the week before when the exam actually is scheduled and so forth. So make efficient use of your time regarding this in particular, because we still have a few more weeks until exams start and so forth. So it's possible for us to actually get in some live practice sessions if requested. And you can request these via email, you can request these via the forum. That's perfectly fine. I will schedule accordingly to make sure I'll be here in order to do these sessions as required. Alright, so good luck on your final exams. Hopefully you guys get through with everything. The exam is going to be pretty straightforward, so there's nothing to be worried about. It's going to be 12 hours as far as I know, and it's just going to be 5 questions, each with 20 marks. And all the materials for the lectures here are basically pretty straightforward with the example questions and the problem sets and then the slides. So once you did these and you have a good idea of how to do these yourselves, you're pretty much set for your final exam. There's not going to be anything to worry about and so forth. Alright, so like I said, good luck on your final exam. So take care, be safe, and hopefully I'll see you guys soon. Alright, later.